So this is the ultrasound that we've been using. We got this on loan from Butterfly Ultrasound. So this is it in my hand for scale. And on the right is an actual ultrasound. At the top, you can see a bit of the probe. And then down here, you can see something that's definitely not a tumor. This is the cross-section of a French's mustard bottle. So that's your primer for what ultrasounds look like. Good luck.
If you weren't able to tell, I mean,
Yeah,
it's pretty obvious.
It's pretty obvious, really. Come on.
Yeah, and what's exciting about ultrasound is obviously it has a huge number of applications, medical being one of the main ones, and it's an inherently a very sensory motor way of clinicians understanding what they are seeing. And it's very challenging to use AI for this because in the medical field, you generally don't have large data sets. There's lots of reasons that Monty would be perfect for this kind of use case. But ultrasound is not a very intuitive modality, at least if you're first dealing with it. So, this is, for example, what the 1,000 Brains Project mug looks like in ultrasound, or part of it, rather. And what you need to bear in mind is that ultrasound, the probe is producing a two-dimensional beam, like a fan. But that two-dimensional fan is moving in three-dimensional space, kind of going through a structure. And as the name implies, the probe is emitting sound waves, ultrasonic sound waves. And basically the time it takes for that to bounce back tells you how far away something is. And the intensity tells you kind of how white that is. So something like bone or metal or ceramic, like we were dealing with, tends to show up as really intense, really white, whereas kind of soft tissue and things like that appears more gray. And then water would just generally appear like black. And so that can give you a huge amount of information, but it is challenging to work with. So, for example, the TBP mug, as I was saying, this is an image of it. And in particular, it's an image, a 2D plane kind of going through the side of the mug and the side of the handle. And so what you're seeing here, for example, this is the top of the cross section of the handle. If you can imagine you had like a very sharp saw that went straight through here. This would be what the top of that would look like, and this would be the top of the side of the mug. But you don't necessarily see everything you would expect because, for example, you get what are called acoustic shadows, where the sound cannot continue to propagate, and so it's black behind this edge. And you also get lots of artifacts. So these can be caused by various reasons, but if the sound wave gets delayed, if it gets reflected multiple times, all this kind of stuff, you can basically the image kind of hallucinates. As far as the probe is concerned, it thinks there's objects out there in the world. And so these were kind of some of the things we had to deal with when interpreting these images.
So it also turned out to be quite a lot of moving parts to setting this up. So I'm just going to talk you through the architecture diagram really quickly. So over on the left, we have the ultrasound device. To it, we strapped an HTC Vive location controller with just a piece of Velcro. When you click the button on the probe, it captures what the probe is currently looking at and sends it to Monty with some metadata about the depth, the scale that we were looking at on the image. At the same time, the HTC Vive controller is streaming its location to two sensors on the floor, which then send them to, not pictured here because it was even more complicated, which is then streamed to the HTC Vive service, where it stores the current orientation and three-dimensional location of the probe. As Monty processes, it gets that image and then it asks the Vive service for the data, and then it visualizes that over here so we can see what we're actually looking at. It will also suggest where you should move to next. So Monty can't move us, but it could tell us where the next best view to get the next best inference would be from. And then also a visualization of how Monty is doing, what it's learning as we go. And so you'll see all of this in the demo. We want to just give you a quick overview.
Yeah, and so one thing, just to kind of give you a bit of a sense of what the whole thing looks like. So we had what was called a phantom. So a phantom is when you're kind of testing ultrasound or someone's learning how to use ultrasound. And so you have kind of an artificial structure that can be scanned. So, might have an obstetric phantom. But since we were dealing with objects that Monty has learned in kind of simulation, like the YCB objects, we created this setup with essentially a plastic bag filled with water. So, you can imagine it's something like an amniotic sac with objects suspended inside of it. And then all of this kind of set up with some tripods so that we can kind of move around it. And then, oh, sorry, we're basically putting the probe on the surface of this bag with some ultrasound gel so that it kind of gets a consistent propagation of the signal. And of course, the task is to determine what object is inside the bag. And as Will mentioned, we were kind of tracking the position of the probe. The way we did this was with these what are called kind of base stations. These are actually designed for virtual reality gaming. And so people have already spent a lot of time engineering a good solution to this. And basically this tracker, it actually is this tracker looks fairly kind of, what do you call it, static, like it's not doing much, but it's actually looking for kind of invisible lasers that are coming out of these two base stations on either side of it. And that tells where it is, and as well as its orientation in the world, and quite a good amount of sensitivity. So that was really useful for this task.
And so after we basically get the ultrasound images plus the tracking data of where the probe is in the world, we now need to extract some more information from the image. And so this is the processing pipeline. First, we have the environment class from Monty that we customized so that it gets both of these types of information and synchronizes them. Then in the data loader, it actually we look at the full image and try to find a small patch in there, which should be on the surface of the object. So how we do that is we basically start in the middle and move downwards until we detect a significant edge. And then we extract a patch around that. And then from that patch, we detect some point normal and curvature, and we combine that information plus this distance from the top to the patch, plus the tracker pose to get a CMP message to send to the learning module.
So in the demo, you're going to see this iPad app, just to orient you to it. So we have the image here, and then we have kind of the depth that we're shooting at, and the gain is kind of how white this image is. And then we have like the number of images we've captured so far. It starts at -2 because obviously the first two don't count, as we all found out. And then like a manual capture button here. We are set to the default type of musculoskeletal, which we found was like the best for identifying the kind of hard objects that we have in the demo. So that's going to the iPad app, just so you've seen it.
Yeah, so a bit more detail on extracting the patch. So there were several difficulties. So like the acoustic shadows and artifacts were really giving us some trouble. So for example, sometimes the highest peak in the kind of edge detection is not actually the object. So in this case, we actually want the patch here and not here because this is an artifact. And so we had to do quite a bit of fiddling to figure out the right settings and right kind of algorithm to get the patch off the surface. And then next, we basically figure out a bunch of points on that surface and try to fit a circle through those points. And that circle tells us about the curvature at that point. And then we also try to estimate a point normal at that center location, which can tell us about the pose of the patch. And that also took a bit of fiddling because, again, there are all these little artifacts that sometimes get these blue dots to show up in the wrong locations. We had to kind of sometimes limit the range in which we try to fit the circle because like surfaces like on the brain are very bent. But yeah, eventually I think now it works reasonably well. And then we have to combine the depth, the sensor, and the agent location. So if we just look at the agent location, so just what the HTC Vive returns, we basically get the shape of the bag. And then after we add the depth that we extracted from the patch and the kind of offset between the probe and the tracker, we get more something that's shaped like a mug. If you have seen it many times, you see the mug, but if this is the first time you see this, you might not recognize it.
It's not a tumor.
Yeah. And then we added
but it could be a lot of other things besides a mug.
But yeah, so if you visualize it as 3D, so you can kind of rotate it. You can't see it on the slide, but if you rotate it, you see that this is the body of the mug, and then down here is the handle. It's a bit hard to get a good screenshot of it. But yeah, it does look like a mug. And then we added a bit more live visualization that we can run during an experiment so you can see what's going on. So we have the input image and we have the extracted patch. You see how we fitted a circle through that patch and a point normal there that we extracted. And then that gets combined into locations and orientations in a common reference frame, so like relative to the world. And over time, while we move the probe, so each of these blue dots here is basically Niels moving the probe to a new location and taking another picture. So over time, you kind of have a bunch of points and they update our hypothesis space. And then eventually you have a most likely hypothesis and a couple of other possible objects. And eventually you hopefully recognize the object, which in this case we actually did. Even recognized some symmetry in the potted meat can. Yeah.
Yeah, and another thing that we wanted was to be able to show to the user, the person who's kind of operating this, where the probe is relative to this bag, that's kind of suspending the objects. And the reason we want to be able to show this is because, as you'll see in a moment, we also want to be able to direct the user where to move the probe. And, going into the farther future, if Monty was ever used, you can imagine someone who doesn't have a huge amount of training in sonography, if they can just figure out how to move the probe and they can get some direction about where the probe should move, then that could enable them to acquire some quite high quality images with guidance from Monty. But the first step in this is actually showing it, okay, where's the probe right now? And so that's what you're seeing kind of here, how we have this visualization of the kind of bag as this kind of cereal box like white rectangle, and then the probe as this blue rectangle. And you'll see this kind of live soon. But as the probe moves in space, the position of the probe in the visualization gets updated. But in addition to this, we can occasionally Monty reaches a state at which it thinks there might be a goal state that if it moved to, it could reduce uncertainty about what it's seeing. And this is what we call a goal state. And so that's what the visualization is showing here, is that at that point, this new blue arrow comes in, and that's basically telling the user, you should move the probe into this location. And basically that blue arrow will continue to be there until the user has moved the probe there. It's still up to the user to decide whether they acquire an image there or not. Monty doesn't force them to do that, but it's at least giving some kind of guidance about where an interesting view of the object might be to disambiguate what's being observed.
Yeah, issues encountered, as Niels already showed, it's quite hard to work with ultrasound data. When Will and I first got the first images, we were not very optimistic about this week going well for us. But with Niels's expertise, we got something working. Then second one, coordinate transforms are, well, as usual, a huge pain to figure out. Yeah, kind of like Tristan and Rami, you mentioned, like having good visualizations help, but still spend a good amount of frustration and time on that. And then the data streaming was a bit tedious in the Airbnb. The IP addresses would randomly change sometimes, and internet would drop out, and things would go to sleep, like the trackers kept falling asleep.
Or batteries dying.
Yeah.
Forgot to.
So just all the communication was a bit shaky between the 4 different components. We also tried to do a bit more AI-assisted coding, which sometimes helped to get hacky solutions, but also sometimes really did not help. Like it tried to import a module called Monty Python, and it would just hallucinate some funny things. We could not resist that temptation to eat some of the data set. Tried to make a good case for why it doesn't matter if the hot sauce is filled or not. So it was open.
Doesn't affect the ultrasound image.
Yeah. We also had a magnitude 6.2 earthquake at 6 a.m. in the morning that woke us up. And for a couple of hours, we were debating whether we should go into the mountains because there might be a tsunami. Luckily, there was not. And some family emergencies of kids falling downstairs.
Downstairs.
Oh my.
She's got a black eye now.
Yeah, and I guess there's a lot of kind of interesting things you could do in the future. In terms of kind of shorter term things that we'd love to look into, a big thing is the challenge of getting kind of reliable features extracted from those images. And as kind of Vivian was alluding to, if it picks up on an artifact and it thinks that's the edge of the object, then in general, the representation's totally off. And there's a variety of ways we could kind of handle that better. One thing we don't have at all is, we're just kind of looking at the ultrasound as these kinds of images in 3D space, or sorry, edges in 3D space. And that is important for how humans understand ultrasound images, but it's also only part of it. We also look a lot at what is the kind of actual texture of what you're seeing. So, whether it's a lung or gallbladder or whatever, all these things will look very different. And it's true of the objects we were scanning as well, but that's not accounted for. Curvature was something we didn't get to being fully integrated. We kind of measure it, but it wasn't in a way that we can compare it to the simulated or the models learned in simulation. And then, yeah, we had kind of some ideas for how we could make sure we get this thing called the kind of maximum curvature dimension, which again was kind of working in principle, but just needs to be kind of made more robust. And then some of the things that we're actually working on the research side, like for example, Rami's working on with kind of resetting, re-anchoring hypotheses, would really help with the kind of robustness of the system. So one of the things we're kind of excited about is we've collected a lot of the images along with the positioning information and saved that, which would be kind of the start of a new data set where as Monty improves on the research side, we can actually rerun it on this kind of real world data set and see how it improves.
Yeah, it's a tuna.
Yeah, but yeah, there was a tuna can in the data set. So that was, I guess, one of the things we were practicing on.
This is Monty you can't see it on the screen, but its most likely hypothesis is the tuna can, which is what's in the bag. And here you can see on the iPad screen, you see the depth, the ultrasound image, and Niels is holding the probe against the bag. And then the data gets streamed to the Windows laptop and to the Mac, and Monty runs here. So that's the whole setup.
Plus a bucket to collect water potentially leaking out of this, what's actually a urinary catheter bag.
So is Monty actually running on the Windows machine or on the Mac machine?
On the Mac.
Yeah, the Windows is only for so OpenVR, which is what is used to track the marker, the tracker. Doesn't really support Mac, or definitely doesn't support Mac, and doesn't really support Linux either, especially like a headless Raspberry Pi without a GPU and all that stuff.
Yeah.
All right.
Okay. So how about answering the two questions?
Can you please remind me again?
How it shows Monty's capabilities is that it's like a very kind of shape-based approach to recognizing objects. It's not just like low-level features that it picks up, which it couldn't do much with in this ultrasound data. It's really about moving a sensor in space and getting locations relative to each other in space, which Monty is uniquely made for. Then also this kind of goal state generator that Niels showed with the point that tells the user where to move the probe next is Monty's intelligent action policy, where it uses its internal models to tell you which view would help most recognize the object. So it's not just like a random policy or like a methodical scan as any current ultrasound AI solutions are, but it's like very methodical about acquiring the information it needs.
Yeah, and then in terms of the kind of the long-term future applications, so of course it's not ready to be used now, but with improvements and with improvements to Monty, this could be a huge help for kind of bringing ultrasound to parts of the world where any kind of medical imaging is hard to do. Ultrasound's amazing because you can hold it in your hand, you can connect it to a smart device, something you cannot do at all, of course, with something like a CT scanner or an MRI. And it's generally safe. There's no ion radiation and all these things. So it's an amazing technology in that sense. The real hurdle is that you need someone who had years of training to know how to use it and interpret it. And so there have been efforts to use kind of current deep learning systems to help with that, but they require huge amounts of data. they don't have this kind of inherently sensory motor or spatial understanding that enables them to suggest acquiring kind of data the way we've shown here. And so, yeah, this would basically be a way to bring the kind of benefits of ultrasound to many parts of the world that currently don't have it.
Yeah, I would echo that. Like the cost of the ultrasound was like $1,000 for an ultrasound. Cost of training a doctor is like $200,000 per year, and then hiring and that's a lot of money. And so the ultrasound devices are going to get cheaper, and it's very easy to get them out to places where they need them. And so I think highlight a point that Neil's made about the lack of training data as well, is that medical data isn't very available, but especially abnormal medical data where there is a problem. Like if there's a tumor on the heart, like we don't have any scans of those because they're so rare, but you need a device or a system to be able to say, hey, this looks like a heart apart from that bit there. So while we didn't get to that in our hackathon, like it was part of the stretch goals, and we think it would be enormously beneficial for being able to scan a healthy thing and then be able to tell the difference between an unhealthy thing without having any additional training data. It would be really cool.
Okay.
Does that answer your questions?
Yeah, that answered my questions.
All right.
Demo time.
Yeah, then it's time for demos. Should we start and we go backwards in order? Or
Sure. Okay.
since we're already
I guess
unmuted.
maybe we can show the
The Benny Hill music.
Yeah, so I'll show around the setup while Will and Niels get everything ready. So yeah, here's our Windows laptop that communicates with the Vive trackers. The Vive trackers are set up down here. There's one, I hope you can see, and then there's another one over there. And Niels is just strapping the tracker to the ultrasound device. So you can.
This is indicating it's on, and then this is connected to the iPad over here. It was a sufficiently complex setup that we ended up creating kind of like a surgical checklist that we would like go through every time to make sure that everything is running. Because yeah, we also have we have the Windows basically running the server, providing the location information. So yeah, so blah, 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 iPad.
While we're setting up, Terry, do you have an object that you would like us to test on?
What about this?
What are my choices?
So we have the TBP mug, we have the tuna can, we have a mustard bottle, the Spam can, we have a package of ramen noodles, we have hot sauce, we have a heart, and the little Numenta brain stress ball. Yeah, I think those are the objects.
Oh. Okay, so why don't we and these are all in your data sets? You already have these?
Yes,
These are the ones you
but-
can use.
You would do us a big favor if you picked an object that doesn't float.
Oh, okay. Okay. Well, the heart probably floats.
Yes,
The brain probably floats.
yes,
Does the mustard float?
A bit, yeah.
a little bit, but we can try it, right? I can-
Well, let me ask you this, what doesn't float?
The Spam can, the mug, the tuna. Oh yeah, we also have some harissa sauce.
Oh,
But Oh, and the
let's go
tomato soup can.
Oh.
with the tomato soup can.
All right, we have never tested on that, so
Oh.
let's see.
It's
No,
I was just going to say the tomato soup can is kind of, it doesn't have a distinguishing feature.
Oh, that's true. And it looks kind of like the cup. So let's go
Yeah,
with
exactly.
something.
The cup has the advantage that it has the handle that kind of.
Okay, how does the hot sauce float?
No, the hot sauce might be a good one actually.
we'll
Let's
check.
do the hot sauce because it has a different shape. And how empty is the hot sauce, Niels?
No comment. Yeah, you may need to hold it, but I think that's a good one actually. Let me just fill up with water.
Yeah, Neil said that he wanted to be like a normal person for once and travel without hot sauce. And then he ended up eating our data set.
Not much control there, Neil.
But I was on holiday for like 2 weeks in America as well, so it was a long time without
Well, America has hot sauce.
not everywhere.
When he told us that it doesn't matter for ultrasound, it was a bit like an addict trying to convince us that.
Yes, yep.
You still have the visualization.
So yeah, as things are shaping up here, you can.
So while you guys get set up, I
Yeah,
just,
wait.
it seems to me all three projects rely heavily on network.
Yeah, I think that's like a robotics inherent kind of problem.
Yeah, okay. Because that kind of eliminates you being able to go to different places in the world with your, if you don't have good network because of all the data coming in, right?
Yeah, if you would
Okay.
design like a full-fledged product solution, I'm sure you could also work with just cables to connect stuff.
Yeah.
So
You
yeah,
can
this
have
is
it
more like
running on
the
a Pro.
quick hacky version.
Okay, so we're gonna start inference.
Are you sharing your screen?
Yes, I am.
Okay, cool.
Okay, and then
So did you calibrate the track?
yeah.
Okay.
We've been through the checklist. We should
So right now you'll be seeing you can see the probe. Sometimes it gets a bit laggy when we're on Zoom. Unfortunately, there's just too many devices running. But the kind of probe moving relative, and then maybe if you switch over, Will, to the other view, what we have here is a view of.
Try and make it full screen.
What do you call it?
Yeah, on the top left, you see the full ultrasound image, and then next to it, you see the extracted patch and the features that we extracted. And then to the side of that, you saw the relative locations in the world that it estimated. And then on the bottom row, you can see Monty's current hypotheses of what it thinks it is sensing. So there's still, almost all of the objects are still possible, but the most likely hypothesis right now is Monty's heart. What did we actually put in?
Change that. The hot sauce.
Hot sauce, okay.
So we have, in our kind of experiment setup, we have 30 steps to try and correctly.
Maybe see if a gold state appears.
Oh yeah.
Not yet.
Okay, sorry. The ultrasound just needs a lot of jelly and fluid to work properly. Any air and it doesn't see anything.
We're not 100% sure yet that all of the coordinate transforms are correct.
Yeah, there's
So
definitely
there might be some room for improvement.
Can you use Vaseline?
Sorry?
Never mind.
what top hypothesis we have at the moment.
The mug.
Interesting. That's surprising. Yeah, it probably is the case that the coordinate transforms aren't totally right, because this should be doable for Monty.
Yeah.
We just have a few more, like a few more observations. Oh yeah, did we show the goal state? Sorry, if you go back. Do you see one?
Yeah, no.
Okay. Never mind.
Seems like the tracker
The
probe
tracker
is
is
not
very
calibrated
awesome.
right.
It's oh yeah. For what it's worth, that's just for the human. It doesn't affect the data collection.
No, there is a suggested pose up here. You want to have a look at it?
Okay, yeah. If you rotate, so yeah, I guess that was
Stick it in the
before
bag.
calibrating, so maybe it's really off. But anyways, you can see the principles operating as well as the coordinate transforms that are clearly still in need of debugging. How many steps are we on now? Okay, I'll try and be a bit quicker. You can kind of see on the ultrasound image, like at the top, these like zebra stripes. Like that's just one of the kind of artifacts that comes in, and we have to kind of.
Are those reflections or something?
Okay, there we go.
And we finished.
Yeah, it's kind of like bouncing back and forth and creating like a false image at a certain depth.
So what did it categorize? Monty's hard.
Monty's not.
Oh,
Oh, that's a shame.
oh well.
Well,
You
next
can try
time
multiple times, right? Or no?
we can try
multiple,
another
but-
object. But maybe you first demo yours.
Yeah.
If you also get it wrong, then we can have a tiebreaker.